Let's find the surface area. The portion of the surface C equals 16 minus x squared minus y squared in the first octant. Now recalling what these surfaces look like back from chapter 11, we have Z equals 16 minus x squared minus y squared. This is an elliptic paraboloid that actually opens down. To sketch a 3D image of this, it looks something like this. Imagine you have this elliptic paraboloid. It opens down. We want to find the surface area, just the portion of that surface that lies in that first octant. And we need to determine that base region. Looks like I can't sketch the yellow, but we want to determine this base region here, and then the surface area is the portion that lies above that. To determine that base region, we want to find out where this elliptic paraboloid actually intersects with the xy plane. And it intersects in the xy plane when z is equal to 0. So if we set this equation z equal to 0, we get 0 equals 16 minus x squared minus y squared. When we rearrange this, we get x squared plus y squared is equal to 16. And we know that's the equation of a circle. It intersects in this circle with a radius of 4. So we can sketch the two-dimensional base region. Just the portion in the first octant corresponds to the first quadrant. And we're going to graph a portion of a circle with a radius of 4. X squared plus y squared equals r squared, so the radius here would be 4. So this is our base region. And again, recall the formula for surface area is equal to a double integral r. Well, this is r is our base region, where we have the square root of 1 plus the partial derivative with respect to x, that quantity squared, plus the partial derivative with respect to y, that quantity squared times your differential area. So let's find our partial derivatives. Again, z is a function of x and y. So the partial derivative with respect to x of this function is equal to negative 2x. The partial derivative with respect to y of this function, treat y as a variable, x as a constant, that's negative 2y. We can make those substitutions into the formula. It's going to be a double integral of the square root of 1 plus this negative 2x when we square it, we get 4x squared. This negative 2y when we square it, we get 4y squared times your differential area, dA. Now we can write dA, the differential area, is dy dx, dx dy, or even r d theta and r d theta dr. So I think that's going to be a good choice here if we use r's and thetas and determine our bounds in terms of r and theta. To determine the bounds for r and theta, our smallest r, let's erase some of that here, the inside radius, or the smallest radius, would equal 0, and this is a circle with a radius of 4, so the outside radius is equal to 4. Then we need an angle, our smallest angle, starting off at theta is equal to 0, and then continuing on counterclockwise until we get that region. The largest angle theta would equal pi over 4. No, pi over 2. Sorry about that. So we can set up the bounds of integration. We should determine what order and also make the substitution. 4x squared plus 4y squared, using the substitution equations, conversion equations, we know x squared plus y squared is equal to r squared. So if we have 4 of these x squared plus y squared, then that's the same thing as 4r squared. So we're going to be making the substitution here, the square root of 1 plus 4r squared. And then our differential area, since we're using r's and thetas, could be either r times dr d theta or r times d theta dr. Since it's r simple, theta simple, I can choose either way. I'm going to choose d theta dr as the order of the differentials. And then the inside bounds of integration would be for theta, which goes from 0 to pi over 2. And then the outside bounds would be for r, which goes from 0 to 4. You can evaluate the inside first, treating r's as constants and thetas as variables. You can integrate that, evaluate the inside integral, and then you have it get it to a single integral. Use a graphing calculator to approximate, or you can use u substitution to get that the area is approximately 36.2. So what we have found is we found the surface area of the portion of the surface, c equals 16 minus x squared minus y squared, that lies in the first octant. So that portion of the first octant lies above this region in the first quadrant, and we found that by setting this z equal to 0. That's where the surface intersects with the xy plane, so that's going to be our base region R.